energy per bit in 2D. So in a two-dimensional signal space, it's worth remembering what energy per bit actually is. So, or energy per symbol, excuse me. If I can write energy per symbol, remember, as the sum, as basically the average energy in each of the signals. So this is the sum over the probability that I was sent of the energy in I. So what is the energy in I? From weeks ago, we argued that it's basically the sampling time times the sum from I equals 1 to NB of the coordinates squared. Like so. So if I take each EI, I send the ith bit with the waveform SI of k, this is the definition of ES, or of the energy in the ith symbol. Like so. We could re-express this. Remember, I prefer to talk in terms of vectors now. Now that we're talking about signal space, I prefer to talk in terms of vectors. So I transform this signal into the vector SI. So is there any way to express this in terms of the vector rather than the signal? So basically what I'm doing is I'm taking each, I can actually rewrite it directly. Let's say TS times the sum from I equals 1 to NB of signal I, the J equals 1 NB, signal I, the jth coordinate. So if you think of SI equals SI1, SI2, SI3, and so on up to SI and B, then this is certainly true. So what am I really doing if I'm taking a signal and taking each coordinate and squaring it and adding it together? Let's think of this a different way. Sum from J equals 1 to NB of SI of, let's say, S1J, S2J. What operation does that look like? Taking each coordinate of a vector, multiplying them and adding them together. What does that operate? It is dot product. So this is dot product of SI with itself. Which is what? Want to express that in terms of something else?
Norm squared.
Norm squared. So basically, if I take the norm of this vector squared, that multiplied by TS is the energy in that signal. Okay. Now, what is SI in two-dimensional signal space? SI in two-dimensional signal space is alpha I Sx plus beta I Sy. So this is an orthonormal basis, and alpha and beta are the ordered pair of coordinates in the vector space, in the signal space. So what I'm going to do is I'm going to say energy in I is equal to TS norm SI squared, which is TS times SI dot product SI, which is TS alpha I Sx plus beta I Sy dot alpha I Sx plus beta I Sy, which is TS. Okay. Dot product is like multiplication in that it distributes over addition. So I could say TS alpha I squared isx dot sx plus, I have alpha isx dot beta isy plus beta isy dot alpha isx, so I can write that as 2 alpha I beta I sx dot sy plus beta isy dot beta isy, that's beta I squared sy dot sy. This is equal to ts alpha I squared. Okay, the norm of, a vector dotted by itself is equal to its norm squared. Sx dot sy is what? 0, because they're orthogonal. And beta I squared, norm sy squared. Okay, what is the norm of sx squared? It's an orthonormal basis. So this is 1, and that's also 1. So this is therefore equal to energy signal I, therefore equal to Ts alpha I squared plus beta I squared. So that's kind of neat. It's neat for 2 reasons. So first off, norm S, so basically this is the length of the vector in vector space. That's the first reason why this is neat. Length squared. In signal space. But the norm of SI is also in some sense the length. So therefore, norm SI squared is equal to the length squared. So in this, it's interesting that this is length, and then when I transform it into signal space, I still get that the norm of SI is equal to its length. So I mean, this is 2-dimensional length of a vector. We're all familiar with how this works. Like that. This is the length of a multi-dimensional vector. That's less clear, but it's neat that you get the same answer. Okay, and to finish it off, same as in the 1D case, energy per symbol is equal to the sum of probability of I times energy in I, and then energy per bit is equal to energy per symbol times however many symbols per bit, which is equal to energy per symbol times 1 over the number of bits per symbol. How many bits are there per symbol? Log 2 of the number of symbols, which is m, so that's ES over log 2 m. Just as an aside, if you don't have log 2 on your calculator, do you know how to calculate log 2? Yeah, so if you have natural log or log base 10, or it doesn't matter what, it is log 2 of m. Is, let's say, natural log of m divided by natural log of 2. Excuse me. Okay. Any questions on that? Do a quick example using our 8 ARI